Okay, hello everyone. Can anyone say online if you can hear me?
Yeah, I can hear you. Can you?
You can hear me?
Yes.
Yeah, okay, good.
Yes,
Okay.
good sound.
Okay, thank you very much everyone for coming. My name is Daniel Yurchenko. I'm a member of the Institute of Sound and Vibration Research, University of Southampton. And I will talk today about energy harvesting from vibro impact motion. In particular, I will talk about vibro impact pair. That's a special type of the vibro impact system. And I will focus on basically two things. One is how we can get energy out of such a device. And secondly, it will be a little bit more mathematical, maybe a little bit more confusing for students especially, but I will talk about grazing and competition between classical, which I called smooth, and non-classical, which I called non-smooth bifurcations. Okay. Okay, so just this a brief outline of my talk. So I'll talk about what is the electrostatic energy harvesting and how we can use the electric materials for that. I will then present the concept of the vibro impact energy harvesting device. And I'll talk about how it is possible, although this system is very complicated, to find some analytical solutions and the results. And then I'll talk, this mathematical part will be about the stability, the grazing motion, and different types of the bifurcation. And then I will, if I have a time enough, to tell you about the effect of the asymmetric restitution coefficient on such a system. Okay, so basically, for those of you who don't know, what is the electrostatic energy harvesting? Basically, the idea is very simple. It comes from the fact that if you have a capacitor, okay, then the charge in the capacitor, which is the Q, is proportional to the capacitance C, and V is the voltage. So traditionally, what we learned is that for the given capacitance, we change voltage and we get Q. Now, in energy harvesting, what we can do is actually we can change the capacitance, because the capacitance, as you can see, is proportional to the some coefficients, which is the epsilon, which is the permittivity of the material, and then volume on the top, and the z square is the distance between the plates. So if you mechanically start changing the plates distance, if you move one towards another one and apply voltage, for instance, then by reducing Z, you will increase capacitance. And then when you go back and let it go and the Z goes back basically to its original position, whatever you generated extra can be harvested. So that was originally done, this idea. I'm not even sure who was presenting this idea, but it was coming definitely from electrical side people. And that was not very simple thing to do in terms of the implementing this physically, okay? So what are the good and bad things about this type of the energy harvesting? So the good thing, it's a very high power density. So it's a order of magnitude bigger than piezoelectric energy harvesting, which is very popular. So that's a good thing. The little bit, problematic thing is the initial voltage, because as I told you, you need to apply voltage to harvest more. And the more you apply, the energy will be proportional to the square of the what you apply. So if you apply 100 volts, the output will be proportional to 100 square. But if you apply 1000 volts, it will be already proportional to 1000 square. So you're gaining a lot. So the higher the charge you put, the better. Now, what happened is air has a very, very low dielectric permittivity, which is epsilon. It's equal to 1. So people start thinking about, well, what if I do this not in air? Can I improve this somehow? Because you can see capacitance also depends on this epsilon. And therefore, people come up with the idea of using a dielectric elastomer. So these are very specific materials which have a very good stretching rate. So this is something like silicone. You know, you have probably dealt with silicones. You have a silicone in your bathtubs, and so on. So you can stretch it, 300-500 times, and it doesn't break compared to metal, where you can stretch, 3%. So that's why people decided to use such materials, because you stretch them a lot. When you stretch them, you basically increase the area, reduce the thickness. So in this sense, you're changing the capacitance, And then when it's maximum, you apply voltage. When it's minimum, when it's getting back, you basically harvest energy. So this is a very simple idea. You can see here on the figures, the left one and the right one, that's how we do that. So you push it, you press it, or you stretch it in some way mechanically, and then you let it go back to its original state. Okay, so and as I mentioned, that should be probably come much earlier, that the dielectric permittivity of those materials are so high that they could reach up to 100 compared to 1. So you can increase this a lot using special type of the nanotechnologies people have. Okay, so how people try to use it? Well, as I told you, the main secret is if you stretch it properly, then you can apply voltage and you can get back energy. So you can stretch it in plane, which means that, you know, you do just a uniaxial or biaxial stretching. You can do radial stretching, as you can see here on the figures on the right over here. Or you can do out of plane stretching. And the out of plane stretching, one of the idea was people use it for energy harvesting from waves. So this thing is called oscillating water column, and probably you can guess what happens here when the wave comes. The level of water in that chamber goes up. It pushes the air, and the air pushes the membrane, and the membrane starts ballooning. And when you balloon, you decrease thickness, you increase area, so you change the capacitance. Okay. So that's basically a very simple idea of how people try to use it in terms of the, how to collect energy. Now, I'm going to show you the one issue which is overall related to this type of the energy harvesting is you need to create very stretchable electrodes, which means that your electrodes should stretch as much as your material. So what you can do is the following. You can use the multi or single wall carbon nanotubes. That's a tiny hairs, which are as long as 100 micrometers and as thin in radius as some nanometers, okay? And when you put them a lot, they basically, overcome each other so that when you stretch it, there is a still connection because carbon is good electrical conductor. So when you stretch it, they're stretched, but the connection is still there. So you can see on this video, we have such kind of you will see it in his hand. You can see that there is a
now we are going like from
membrane there, and we push the membrane, and you can see how capacitance goes up. So it goes from basically original 30 picofarads goes to back to 168 picofarads and back. So that shows you that that's a very good, cover we have in terms of the electrical conductance. Okay, so basically that shows you in the video that it is possible to build it and it is possible to use it. So now let me go to the stage of how we decided to use this in terms of the energy harvesting. So you can imagine this is the slice view of a device where what you have is the capsule, which is in green, basically, yeah? And that capsule has a form of the cylinder. And inside of that capsule, you have a ball, okay? So when this capsule is excited, okay, the ball goes and impacts one of the sides here, which are written in or which are shown in orange. And those are the dielectric membranes as I show you. So every time when you have an impact, this ball stretches the membranes change the capacitance, you apply the voltage. As soon as the ball goes out, you take energy from this membrane, okay? Now, the dynamic of this is actually very simple because, first of all, we assume that there is no damping inside, or at least we can assume that because if you have enough force, damping is very slow, we can neglect it. And then the motion of this, the capsule itself is subjected to the harmonic excitation. So that's why you have a Z double dot equal to harmonic excitation divided by mass. So there are no springs or anything else attached. However, you have also the ball, and the motion of the ball is also, you don't have anything attached to that ball. So basically, it's a ball is in free motion unless it hits the membrane. Okay, so therefore, for the motion of the ball, we have a g times the sine beta. Depending on the angle, the gravity could be in full, or it could be zero if the device is horizontal. And then the only thing which connects them is the moment of the impact. So every time when the ball reaches half of the distance left or right, the ball will be impacted by the membrane. So basically, the membranes excite the ball, and at the same time, they are deformed, so that you have a change in the capacitance. Okay. Now, this is called impact pair because the both of them are moving. So there is a relative motion between them compared to the vibroimpact systems where usually you hit one of the stationary wall or stationary limiter. That's why we call this a pair. Now, the dynamics of this is actually very, very interesting and complicated, and I'll talk about this a little bit later. But the main thing we assume here is that the impact happens instantaneously. So basically, that gives us a right to use the Newton's law for the restitution, which means that the velocity after impact is equal to minus, because it goes to opposite side, coefficient of restitution times the velocity before impact. Okay, but if you want to harvest energy, you cannot use it because in this formula you don't have a stretching of the membrane. So to use this from the electrical point of view, we need to actually consider the membrane stretching. So what we do is we use pure geometry here. We know that the ball is spherical, everything nice, has a radius. So when we impact the membrane, you can see that the ball goes through a number of stages. And we can calculate basically this is kind of a conical shape which is created by the ball, knowing how far we go inside of the membrane. And then if we know how far we go, because the material stays the same, that means that we're changing the area and the thickness. So to know the area, we basically calculate the two areas. One is basically which is going along the ball, and then the other two areas here are basically the conical shape areas. So when we connect all the areas together, then we know what is the extended or stretched out of plane area. And then based on the conservation of the mass of the material, we can calculate what is the thickness at this stage. And then the only thing here we need to know is how nonlinear the material behavior is. And that's nonlinearity is basically modeled in the last equation here with the power n, because the material behaves a little bit complicated. It behaves like a softening a little bit and then going hardening. So the x here is, or n, x in power n, where n is not 1, but actually it's closer to the power 3. So this is how we calculate the amount of energy or voltage we get from these impacts. Now, this is the typical picture. What happens if you use the ball? So you can see on the left side here, this is the motion of the ball in blue. And then in the red dash, we have a motion of the capsule. Okay, you can see the moments of contact. On the right side here, you can see this is the velocities. So you can see that the ball travels freely without any forces. Then you have a horizontal line. And then at the impact, the ball changes the direction. So you have, again, free motion, and then again, change in direction. On the left side, you can see that because this is ideal motion, every time you generate the same amount of energy, or basically voltage. So the initial voltage we apply was 2000 volts. And then you can see that we generate about 2320 or 2330 volts. So that's how much we generate. And on the right side, you can see this is the state space domain motion. So you can see that the ball travels free and then impact and then travels free again and so on. Now, if you start changing the parameters, which are basically the restitution coefficients, the excitation and the amplitude and excitation frequency, and also the size, the distance of that capsule, then behavior can be very complicated. So, for instance, this is another option. When we increase a little bit amplitude, you can see that behavior now is far from being very simple. So it gives us some different types of the harmonic and the motion. And you can see that on the right side at the bottom here, you can see that sometimes we have a very, very low power impact, low velocity impact. You generate very little bit of energy here. And then on the right side, sorry, on the right side, On the another moment, you can generate up to 4,500 volts. So you can see that depending on the force or the impact momentum, you get different amount of energy there. Now, what happens is, I keep getting different types of notifications. So what happens is, although the system is very complicated, it turns out that you can find easily exact solutions. So it will be not purely analytical, but it would be semi-analytical in the sense that you can find the solution, but then because you get the equations which you cannot solve analytically, you have them solved numerically. Okay, so we call it like a semi-analytical because it's exact analytical but solved numerically. So basically what we can do is we can introduce a new parameter, which is the z here, and z is the difference between the motion of the ball and the motion of the capsule. And then when you integrate it, basically you can build with so-called maps. So the map is how the ball goes from the left membrane to the right membrane, for instance, top to bottom. And then there is some condition for the velocity, because remember the restitution coefficient is less than 1, so you have a changes in the velocity, and then you have a map going back from the top to the bottom again. And by combining these maps, you can build different types of the motion. So the one simple one type of the motion is 1-1, which means that you have a one impact against the bottom membrane and one impact against the top membrane. But you can have a more complicated motions like 2-1, like a two impacts against one membrane and only one against others. Okay, so basically by combining these things, you can do a lot, but still you need some numerical solution to do that. Now, what's important here, and now I'm coming to a little bit more complicated part, is that here d is the coefficient which is non-dimensional distance. And that's important coefficient because s on the top is the actual distance or actual size of the capsule between the membranes, and the a at the bottom is the amplitude of the excitation. So when I use d parameter, I can do it in two different ways. I can keep my amplitude of the excitation and change s, which is the physical distance, or I can keep my s and change a, which is the amplitude of the excitation. So that's why in a few plots later, when I show you that, you should remember this, but I will have this formula separately again. Now, when you do this, and you do, for instance, a map like a P1, which is bottom to top, and then P2, which is the top to bottom, as I told you, you build the equations, which then you solve numerically. And then when you solve them numerically, basically, you can choose the proper conditions based on the bifurcation diagram, which I show you a little bit later, to build different types of the motion. So, for instance, you can see here the symmetric motion, which means that on the way from the bottom to top and from the top to bottom, you can see the motion in the state space is very symmetric. So you can clearly see the symmetry in even the time response here. But you can also build asymmetric type of motion. For example, you can see here that from the left to the right, it goes more or less straight. Whereas if you go from right to the left, it has some peak here, which is going to a little bit low velocity and then gain the velocity again. You can have even more complicated motion depending on the angles of the inclination. Remember that beta is the angle of this device. You can have this type of or you can have some kind of a bifurcations, which I'll talk about later, which is called period doubling bifurcation. So instead of having, one period over the period of the excitation, you will have two periods of the response over one period of the excitation. So you can see here, this happens at the bottom slide. So that's a T periodic motion. So then what we can do is, because we have basically analytical formulas, we can build the Jacobian, and using the Jacobian, we can actually use the linear stability analysis to build the bifurcation diagrams and what happens. So for instance, this is one of the simple bifurcation diagrams, which is on the left, you can see for the velocity of the system. This is for the phase of the system. And then the next one is for the time takes the system to travel left and right. And you can see that D is my parameter of the bifurcation. And basically, if I want to know what's going on, I simply need to calculate the eigenvalues So whether they are positive or negative or crossing some certain values, and then I need to know the determinant of this matrix. And if I do that, I can calculate different types of the bifurcations. For instance, I can find the period doubling bifurcations, or I can find fold bifurcations, for example, when we spot this. And then basically when I know what happens, then before that bifurcation, I have a one type of the motion, and then right after the bifurcation, I'll have a different type of the motion. So you can see here, the motion is symmetric because you can see that the velocity values are basically identical. So these are the top branch means that velocity against one membrane, and the bottom branch means there is a velocity against another membrane. So basically it's a 1-1 motion, and you can see that if I start increasing d, then my velocities will be bigger and bigger because the ball travels freely, so it basically gets acceleration and gets extra velocity while it's traveling longer distances. Okay. So if you have asymmetric motion, as I showed you before, this is a very simple example of the asymmetric motion. You see that velocity, for instance, going to the bottom is higher than the velocity going to the top. Yeah, so you can see, but it's still 1-1 motion. Now you can have a more complicated types of the motion, which is in this case is a BB means bottom bottom, top bottom, which means that two impacts against the bottom membrane and top, and one impact against the top membrane. So you can see here, for instance, in all this diagram, you can see how the angle beta may change, you know, the range of the values where you have a stable 2-1 motion. So you see that for the higher values of beta, which is pi over 2, this range is a little bit short, you know, and then if you increase to, decrease the angle, this range will be increasing, and you will have even some other types of the motion here where you have some bistability and you have different types of the bifurcations, which I'm going to talk about next. And of course, remember that the main point of this all is energy. So you can calculate the energy based on what type of motion you have. So if you look at those plots, you can see that we use two types of the measures. One is very simple one, which is the average energy over time, which is here shown in cyan, light blue. And the other one, which is not less important, is the average number of energy per impact. Because ideally, you don't want to have too many impacts because every impact gives you some wear of your membrane. Your membrane gets worn more and more. Okay, so you want to get best out of less impact. So that's shown in red, and you can see that, for instance, in a case of 1-1 motion to the right here. So this is energy produced, the top branch blue, energy produced by one membrane, the green one is energy produced by another membrane, and the cyan one is the average energy produced by the entire device. And then you can see that the red one here, it has a jump here down because simply you have one extra impact. So you're producing very little energy with this impact because it's a low velocity impact, but number of impact goes from 2 to 3. Okay, so that's why you have a less energy per impact. Okay, so now I'm going to a little bit more complicated part, and that part is related to the fact that when you do randomly take any values of the parameters, what happened is there have been lots of papers where people talk about the fact that sometimes you can observe some bifurcations and sometimes you cannot. So some type of motion you can observe and some are not. And you can clearly see this from these four figures. So for instance, you can see in the figure A that when you have a 1-1 motion, the next to the left, when I start decreasing my D value, what happens is you go to the 2-1 motion through the so-called grazing, which is called G here, okay? So you get a grazing from 1-1 to 2-1 motion. But if you go to the right plot, for instance, part B, you can see that there is no grazing. You have a PD, which is the period doubling bifurcation, which ends up again after the period doubling in period doubling where with the grazing together. So basically there is no pure grazing here at all. And then you can see where you have a grazing later in this diagram B when you go from 2-1 motion to 3-1 motion. Okay, remember 3-1 is 3 impacts against one membrane, 1 against another. But sometimes, as you can see, C and D is basically there are no grazing at all. So the question is, so when do we have grazing and when we don't have grazing? And for that purpose, we introduced a number of the things which would be easy for us to later explain the things. So we basically introduced things called ghost grazing, ghost. I hope you know what's the ghost, like invisible grazing. And we also introduced the ghost period doubling, where there is a period doubling, but it's invisible for us. And we put a tilde on top of it so that you can later see, which one is what. And that's very important part, which basically I'm going to explain on the next slide. So to make sure you understand what is the grazing, I'll tell you there is a very simple illustration of the grazing shown here. So the grazing is the zero velocity impact. So basically you touch the wall without actually impacting it. So you're literally getting some limiting case of the zero velocity. Okay, and why is it important? Because you might think, well, it's a zero velocity, so there was no impact. But the problem is that, as by definition of the bifurcation is when your system, where you go through the bifurcation, when your system changes drastically the type of the motion. So here, when you have a zero velocity, before you have no impact, and after that you will have impact. So you're basically drastically changing the system behavior by going through the grazing. Okay, so the question is now, if we know exactly analytically now our equations, and if I put the conditions for the grazing, like at the moment of grazing, my velocity is 0, and I must be at the border of either plus or minus d/2, because that's when the grazing happens, okay? Then I can solve my equations and actually find out exactly numerically where the grazing points are, okay? So what I'm doing then here is very interesting. So what we're trying to do is we go and decreasing the vertical axis, we go down from higher values of D to low values of D. Now, this is the formula, remember how we get D. So I can go with D by reducing simply the size S, and that's what I'm doing in the left column. I'm just going down. And what I can do on the right side is I'm going to increase A. That's on my right side. Now, the first row on the top is where I go from motion 1,1 to something else. So I have a bifurcation. My motion will change drastically from 1,1 motion. And you can see that in blue, we have a period doubling, which I can get analytically easy. And in green, it's a grazing, which I can get through numerically solving exactly my equations. Okay, and what you can see here is very interesting. You can see, for instance, in the first plot, that for the large values of restitution coefficient close to 1, your period doubling is always goes first when we go down, and the grazing goes second, which means that you cannot observe grazing here. This grazing will be ghost, whereas you can observe here period doubling. Okay, if you go to the left and you consider other smaller values of R and a little bit smaller values of beta, you can see that sometimes green lines go above the corresponding blue line. That means that the grazing will be observed first, and your predicted period doubling, although it's predicted analytically, literally you can calculate analytically where it happens, it will not be observed. Okay, so you can see the same happens at the bottom when you basically go through the bifurcations from motion 2,1 to different types of the motion. It could be 2,2, which is 2 impacts, or it could be 3,1, which is 3 impacts against one membrane and only 1 against the right one. So how we can validate this, what we've got? Well, basically, if you look now at the left side and look at my first example when I show you why we go through the grazing, I take the values of beta equal to pi over 9 and very small values of R, very small values of R. So you can see here for these values that basically the grazing here goes above the period doubling. And that's what you observe here exactly on the right plot. In this system, you will see grazing first, okay, and then you will see here grazing second, because the green lines here are above the corresponding blue lines. Okay, now the one point I will point a little bit later is that you can see that grazing typically is the zero velocity, but you cannot see there is a zero velocity at the bottom. You see that the blue line is not reaching zero, and I will tell you why is it. That's very important and interesting fact. Okay, and then for instance, if I take the values a little bit larger to the right, for instance, I take values of r equal to 0.5. In this case, you can see that when we bifurcate from 1-1 motion, definitely we should observe period doubling because the lines, blue lines here are above the green lines. And that's what you see here. You see the period doubling over here. And then if you go to the low values again here, the period doubling line goes first and then it goes grazing. So therefore you can see that you will have a period doubling here again. So the same thing happens when you do increase amplitude. I don't want to take too much time of this because the idea here is the same. It all depends on basically what happens if your grazing line goes above or below period doubling line. Now let us do the following. Let me take the case of the reducing S values and take particular values of the beta pi over 6 and the restitution coefficient equal to 0.3. So you can see this line is shown basically here on both plots. And if you look at this plot, this is exactly what we observe here, and I will talk step by step about this. So if you start decreasing the values of D, you go from 1-1 motion. I hope now you clearly can follow me because you can see one line blue and one green. So this is the stable 1-1 motion, and this is asymmetric motion. You can see the state space plane on the right. And then if you keep decreasing D, what happens is you reach the point where you will have a period doubling, which means that you will see now two trajectories per the same period. So you have a 1-1, 2t motion, okay? And then it's again asymmetric, you can see here, and that's what we observe from the bifurcation diagram, and it's supported by the state space plane. And then what happens is we go into some kind of a turbulent zone, and in this turbulent zone, we call it transient grazing, because what happened is you will have some trajectories which actually have a zero velocities, but generally it's absolutely turbulent. So it could be before zero or just a little bit of inside of the impact. So you can see on this diagram, you have a number of such trajectories. That's why it's a little bit thick and blur over there. And then what happens is we get to the point. So remember I told you why we have a grazing if we don't see actually zero velocity. So what happened here is that before that, at the FB point, we had a bifurcation where we have two basically branches. The one which is the blue one is the stable branch, and the one which is the red one is unstable branch. So you can see that at the period doubling, which we calculated through exact equations, we basically spotted the grazing on the unstable branch. Okay, and that's why we call it ghost, because if you do experiment, you physically will not be able to see it because it's an unstable branch. So your solution will jump immediately to the stable branch and you will have a 2-2 motion. But in fact, your grazing is there. Again, we were able to identify it only because we had the exact analytical equations which we solved numerically. Okay. And then so you can see that if you point specific conditions for this point, which means that you need to provide D, velocity, and phase angle, then you can get one kind of a round of this, which is shown in red, and then you will be off this point because it's unstable. So you will be immediately thrown away to the stable trajectory. And then you can go further. If you keep decreasing the restitution coefficient, you will get to the second point where you get another grazing here, but this grazing basically will have a zero velocity. So in this case, you basically will have an impact with very low velocity, which doesn't produce any energy. So technically, we don't like this type of the impacts because from energy point of view, they are useless, no energy produced, okay? Now, if we go and try to use the same idea and take the point from the case where we increase A value, you can see here that basically you follow this branch. Again, you start decreasing values of D. And what happens is you will follow through the fold bifurcation. You will have a grazing here when you go to the left, okay? But this grazing will be stable, so you will see it basically. And then you will jump to the 2-1 motion. And already the period doubling, which was identified analytically, you will not be able to see. So this bifurcation, we call them ghost in this case, okay? So you can see that the red orbit here going outside of the domain allowable of solution, okay? So that means that you have a not invisible but unphysical solution, which means that physically it cannot be realized, okay? So that's why period doubling cannot physically be observed in this case. And then if you keep decreasing values of D by increasing A, you will get to the next bifurcations, which is the period doubling bifurcation. So you can have here motion 2-1, which is 2 impacts against one membrane, 1 against another, but it's a period doubled, so it's over 2T. So there are lots of complicated things here, and I don't want to go into deep into this too deep into this type of the explanations here. It's mostly just to show you how important it is to understand what's going on. So these are plots when you combine different types of the bifurcations. When you go from the top to the bottom, you can see that you can have here different types of the bifurcation, like things with the tilde, which is the ghost grazing, and the ghost period doubling, where they are with tilde here. You can see stable period doubling and stable stable grazing here, and you can have even transient grazing and period doubling grazing when they coincide together. So for example, if I go for the low values of R here down, first I will observe period doubling, then I will observe period doubling grazing, and then depending where you are, you may observe, you see solid green, it would be grazing. Or if you go to the right, you will not observe grazing, but you will observe this dashed, the blue squares, which are the period doubling 2-1. So basically, knowing this diagram, you can predict what type of the motion you can expect. And then this can be used to build, the device of the proper size for a given amplitude and frequency of the excitations. And on the right side, you can see the same plots. Idea is the same. For the decreasing values of D, we increase amplitude and we see where we will be. So you can see that there are lots of options available when you go from one type of motion to another. So basically, technically, by going over this, we can confirm 4 different types of the transitions from one type of the motion to another. So it could be through first order grazing, which means that you just add one impact on one side. It could be through invisible grazing, we saw that the grazing happens on unstable branch. It could be through the period doubling, which usually is followed by the period doubling together with grazing, or it could be through the transient grazing. And I have 2 more slides just to show you the interesting thing. So the other thing you can do here is, because you can manufacture membranes with the different properties, you can actually have a membranes with asymmetric restitution coefficient. You can have a little bit bigger on one side, a little bit smaller on another side. And you can see what happens, for instance, if I have my RT, which is the top membrane restitution coefficient, is fixed at 0.5, and the bottom restitution coefficient is changed. So you can see that you have a 2-1 motion here because you have a 2 impact at one side and 1 impact on another side. And then when you get the same, you can have some type of the grazing here. You can see that the motion goes, and you can have because this one is not equal to this one, but equal to the second one, it's basically 2-1, it's basically 2T motion. So it went through the period doubling. And then if you keep increasing, you can have a 1-1 motion with this is potential grazing. So by changing only the restitution coefficients, you already can change the system dynamics and the properties. And one of the last slide is basically, this is, again, a little bit complicated, but the idea is the background shows you the amount of energy you can produce. So the more red it is, the more energy you produce. the more blue, the less energy you produce. And again, the idea is that you can see on the left side in the column, you have a small angle, beta equal to pi over 6 inclination, whereas on the right side, you can see vertical placement of your device. And then in the top row, you can have a restitution coefficient on the top equal to 0.5. And restitution coefficient for the bottom row is equal to 0.3. And what we do here is we change the restitution coefficient of the bottom, keeping the top, and we go from top to the bottom because we're reducing D. Okay, so when we keep reducing T, again, you can go through different types of the bifurcations. Here, for instance, on the left side, you can go from 1-1 to 1-1 to T motion. Remember, you have a two trajectories over the time, and then you already have some kind of a reduction in energy here, and then you can go through 2-1 bifurcation and drop it completely. Basically, there is no much energy. Whereas in some other cases, you can see here, for instance, on the right side, for the larger angle, you have this blue spot. So basically, there is not enough energy to produce, there is not enough, basically, energy in the ball to produce two good impacts, because you're basically going against full gravity. So basically, that's why you have some kind of a problem here with the energy, and you want to avoid this region, whereas you can be somewhere to the right, and that can help you to balance by changing the values of the restitution coefficient at the bottom. Okay, so as a conclusions, we have shown very briefly, that is because I can talk about this for a couple of hours if you go into details, but we have shown that there is a definitely competing pattern of different types of the bifurcations. And remember, the smooth bifurcations, which you can get from analytical analysis, easily linear, which are the fold bifurcations, and period doubling especially, it competes with the non-smooth grazing bifurcations, which cannot be predicted analytically purely. There is no formula to follow, but you can predict it because we had an analytical solution which we solved exactly numerically. We also have identified the patterns of how this happens, what goes first and what we can call ghost, and why is it ghost, and so on. We also have identified, as I show you, 4 different ways we can transition from one periodic motion to another periodic motion. We have shown the effect of the asymmetric restitution coefficient, and basically this is all influenced in some way the design of the energy harvesting device, which uses this dielectric elastomer vibro impact system. I would like to acknowledge this work is done together with 2 colleagues of mine. One is from United States and another one from University of Leicester. This work is supported by the joint grant, and most of the things I discussed today, they are presented in the 2 papers. One of them has been published at the bottom, and the one to be appear in nonlinear dynamics. Thank you.
Thank you very much.
Okay, so thank you very much for this nice presentation. So maybe there are some questions or some comments.
Maybe at the beginning, I will ask 2 questions in the name of my students about the input for optimization this system. You use the distance D. If you could try to explain again what is the relation using the draft, how to explain this relation D, and could you define the grazing parameters, the type of output, just for my group?
Okay. Yeah. Okay. So sorry. So basically, again, here it should be actually not D but S. So again, you have a distance between the 2 membranes. Okay. So this distance is S. So S over 2 and S over 2. Okay. And then you can define this non-dimensional parameter D, which basically this non-dimensional parameter D depends on S, depends on the mass, excitation frequency at the top, and at the bottom it's proportional to the amplitude of the excitation, inversely proportional to the amplitude of the excitation. So therefore, you can change the D, which is the design parameter, by either changing the physical distance of the, and that's what we can do, or if you know, we have some environment, like for instance, waves, where the amplitude is changing. So then we can try to adjust, you know, this device for the all different types of the amplitudes which are most frequently met.
So this is a combination of the.
Yes, and then regarding the grazing, again, just the basic definition of grazing is that this is the zero velocity impact, or basically when the trajectories are tangential to the impact boundary. Okay, so that's why the point here, the red point here is exactly the grazing point. So if you don't have this point, you have no impact motion, yeah? But if you have this point, you have an impact motion. Now, in most of the papers before this one, not all, but mostly grazing is studied as a transition from no impact to impact. But because of the vibro-impact pair, there is no impact motion because of the gravity. You will always have at least impact against the bottom one. That's why we study the grazing as a transition from one motion impacting to other type of the motion. But it doesn't really matter from the definition point of view. It could be 5-1 to 5-5. Okay, but it's still grazing if it goes through zero velocity.
Yes, but can we define the grazing as some saturation from portion of energy for change the type of output? I know this is not.
Oh, you mean how it influenced the energy? Yes. Well, I mean, for the energy, grazing is bad because you're adding the.
It's not just discrete parameters. It's not discrete parameters. It can be continuous. Yes, grazing.
Yes, yes. Well, what happens is, let me show you again this this diagram for the energy. So when you go through the energy plots here, so what happens is, remember that all those plots are built for different values of D. So you basically build thousands of those devices and basically check for every value of D what the energy would be. So technically, when you have a grazing, that means you have a zero velocity impact. So this impact doesn't produce any energy, but it changes the motion. So you can see, for instance, from any of those plots that the motion is changed from 1-1 here, for instance, to 2-1. Yeah, you have a blue, green, which is a two impact against one membrane, and you have a dark blue, one impact against another membrane. So you can clearly see that for this type of the motion, my energy value here, which is corresponding to the y-axis, is lower than what I would get for this value of D. Yeah, because this value of D is obtained for 1-1 motion. So technically, when we go through any of those bifurcations to different types of motion, we usually get less, worst case. So you want to make sure that when you build the device, you want to, for given A and omega of the excitation, you want to get 1-1 motion. That's a most productive type of the motion.
Thank you very much. You're welcome. You have some questions. It can be very simple questions because this is the workshop.
Yeah,
So
yeah. Can I ask one
bardzo
question?
proste pytania. Tak na zachętę zadałem też proste pytania. Faruk has a question, but you should switch off.
What is it? Okay, I'm switching, but I don't see the chat, so I need to see chat or.
Faruk is asking, but that's.
Hi, Peter.
What is the
Hello,
question?
Daniel.
Can you?
Yeah.
It's not at the chat. He tried to.
Oh, okay.
So I think that Faruk is going to ask a question. Yeah.
Okay,
Yeah,
go ahead. Yeah, I can hear you.
Yes. Okay, right. So Daniel, so the nonlinearity here comes due to impact or due to the membrane being nonlinear, or it's because of both?
No, the nonlinearity in the basically mechanical study, the nonlinearity comes from impact only because we assume impact is instantaneous. In real life, of course, the behavior of the membrane is also nonlinear, but this has not been taken into account in this study because this study was the case where although we assume that there is some deformation for the electrical purpose, there was no membrane nonlinearity or deformation for the purpose of the studying dynamics of the system.
Okay. Okay. My next question was how damping plays a role here, because when you have this membrane, they are known to be very much damping prone, right? So is there any role that damping plays in the dynamics?
Yes, well, we're going a little bit to the properties of the membranes, but yes, the behavior of the membranes is very complicated. The problem is that the losses and the elastic behavior depends on both how much you stretch it and also on the rate of stretching or the velocity. So basically, technically, that's what we are doing right now is you need to conduct a set of experiments, not quasi-static ones, which usually are done in most of the studies, but actually dynamic experiments with the relatively similar velocities to understand what is the property of the membrane and then use this property to model the membranes properly. But this was just to show you how complicated the dynamic is in general, when even membranes are not considered to be complicated.
Yeah, of course, it was very detailed study, and we can see a lot of parameters playing a lot of roles here. So I was thinking that damping can change a lot of things that we have already seen.
Yes, what happens in fact is that you can imagine that based on even what I presented, when you change R, the R will influence basically your phase angle, and the phase angle will influence basically how much the impact, at what moment in time impact happens, which means it will influence the impact velocity and the amount of energy you gain. But on top of that, the membrane stretching will also be influenced by what is the impact velocity, and losses are also non-linearly influenced by impact velocity. So adding the membranes is the completely new, unstudied issues.
Right, good. Thanks. Nice talk. Thank you very much, Danny.
Thank you for your
question. I don't have any
questions.
more question, Peter.
One question about the initial conditions, because sometimes you have some, you have nonlinear system, you have multiple solutions.
Yes.
Have you also considered such a different initial conditions and basis of attraction in your system?
Yes, we didn't do any basis of attraction, but for instance, initial conditions are very important. So if you could see here, I'm not sure if you can, but on the right bottom here, you can see that, for instance, when you keep changing D here, you will have two different solutions. So there will be bistability here existing. So if you go to the left here, you will be following one branch, and then through the grazing, you will jump to another branch. But if you go to the right, you will be following another branch and then jump to the right branch. So there is a number of the bistability regions, and you need to specifically, precisely input the initial conditions to follow one or another solution. The same thing happens here, basically, not here, but in the next here. So basically over here, what happens is if you keep going to the left, you get to the grazing point and then you jump to another branch where you get a 2-1 solution. But if you go to the right here, you will pass this point and go to the very end of this and then jump to 1-1 solution. So this are bistable regimes here. Okay, so it's very similar to what we have on a Duffing oscillator in terms of the two solutions coexisting, and you jump if you go to the left or to the right.
Here on the graph, you have on the vertical line is velocity.
Yes. Yes.
So is it possible to find some kind of resonance in this velocity, in terms of velocity?
There is no as per se resonance because there are no springs, there is no anything. There are two masses just colliding with each other. So there is no resonance in the nature of that system, but you have a different types of periodic solutions. Yes, but remember again, the elasticity of the membrane is taking into account for electrical purpose, not for the mechanical. For the mechanical purpose, membrane behave as a wall. Yes, it's just a stiff membrane with the different restitution coefficient. Because as I explained again, the behavior, mechanical behavior of the membranes is very complicated. So if you want to study and we are doing this right now, if you want to model this, basically what you need to do is you need not just to take random numbers, but you need to have experiments conducted and then using those experiments fit the proper, data so that you can get analytical expressions for the behavior of the membranes. For beta, so as you can see here, it's very interesting. Thank you for this question. As you could see here, we cut down all our study on 0.1 and 0.9. And we also didn't include case of beta equal to 0. The reason is very simple. The behavior is extremely complicated. It needs to be separately studied just for beta equal to 0, as well as for very low and very high values of R. That's very simple to explain. When you have a very low R, you almost have like a plastic impact. So all energy is absorbed, and it's very difficult to follow what's going to happen. So you need to do a lot of simulations. When R is very close to 1, you have a very, very big transition period. So you almost have, it's like if you consider no damping at all in the system, everything will depend on initial conditions. So that's why those are the values which we have not studied. They give you lots of troubles, and we probably plan to do that separately.
Okay, so any other questions or comments?
Maybe from students? If there are no comments, we can close this seminar. In fact, I could also tell you that tomorrow we have continuation. Yeah. So continuation of the workshop, not this presentation.
Continuation of the workshop, and we start at 2:00 p.m.
according to the Warsaw time, Warsaw Berlin, the European time. Yeah.
Yes.
Okay. So thank you very much, all the audience members, for coming to our seminar and for asking questions and discussion. So I would like also to thank Professor Jurchenko for presenting such nice material. Thank you. Thank you. Thank you, and we can finish now.
Yeah, thank you. Bye all.